Today is finish up a little bit of chapter 6, and we have some homework 11, that will go active right after class. But before we do that, I want to do an angular momentum demonstration with you up here in the front. So let me pause the podcast for just a bit. The full demonstration here with your own eyes, except for a few students coming in late. And so those are similar to the ones that you see in YouTube. I want to give you a couple comments about exam 2 now. And I've invited 2 students with follow-up questions. I hope you guys are ready. And I apologize that the fiasco that we had on Thursday, it was like a triple fiasco, and we just couldn't get the exam printed on paper and over here in time. So what I did was I put all the Scantron questions into exam 2 emergency version, 50. It was going to be 50 Scantron questions and 1 clicker question. So then a calculation. So then I put the calculation as a 5-point bonus in a separate item in web courses, which many of you took. Now, a total of 526 of you guys took the emergency version in web courses. And that is out of 542 in the 2 lecture sections that are officially on the books. So that means that there were 16 students absent, and that's about 3% absentee rate. So that's pretty good. And I was in the first hour lecture, and there's everybody's there, they're all ready, and I made the announcement, that we're not going to have the test, and this huge cheer went up. And I thought to myself, now why are they cheering? And Derry and the other TA explained it to me. You just gave them all another 12 hours to study. So, but you guys did pretty good on the test, so I'm happy about that. But exam 3 is going to be a regular pencil and paper Scantron test. And the final will also be pencil and paper and Scantron plus maybe some iClicker questions, right? So, just bear that in mind. Now, I have a gigantic announcement. It's really important. You should add this to your notes. Matter of fact, you should put this inside the inside cover of your notebook. If you have it, if you're on a computer, if you're taking computer notes, make a graphic and make it your screen background until December 10th. Because we now have a location for the final exam. The final exam is set for December 10th at 1 o'clock to 3:50. Now, the morning section is going to be in this room, but you guys are going to be down the hall in room 201. Now, that's the ginormous lecture hall at the other end. And guess what? Room 201 is the better lecture hall. So you guys get the good one. It's got beautiful windows, and hopefully it'll be a nice day, and you'll be able to. And then when you're done, hopefully it'll be your last exam. You can go out and, just have a nice sunny day. But this section, the noon section, 1 o'clock to 3:50 down the hall in room 201. Now, I'll be shuttling back and forth between both rooms. We'll have extra TAs and a couple extra professors, hopefully. So there should be plenty of supervision and stuff. But it looks, if you've ever been in there, you know what it looks like. If you haven't, it looks very similar to this, except the big bank of windows over there. It's very nice. It's a little bit bigger, too. Okay? Questions about that? Okay. And just to remind you, it's at 1 o'clock, not noon. Our lecture meets at noon, but we'll meet at 1 o'clock for the final. Also, just so you know, it's roughly double the size of a midterm. So it might be 100 Scantron questions and 1 or 2 clicking bonus point activities, or some variation of that. But you have 3 times the amount of time. 60 minutes for a midterm, but you have 2 hours and 50 minutes, almost 3 times the amount of time that you have for a midterm. So the time pressure is usually not as bad as the midterm. Okay, let's get back to physics. Last Tuesday we talked about phase transitions. We looked at this table, melting point, boiling point, and so forth, densities, page 96. We also talked a little bit about heating up substances like water. Now, we didn't have ginormous heating calculations on midterm exam 2, the emergency version. He had a couple little cinchy ones, but they were just involved water. What we're going to do now today is do some deluxe calculations that will apply to any substance. Another thing that we talked about last Tuesday was this idea of e pluribus unum. In other words, the idea that from studying the physics, the theoretical physics of a zillion molecules that you cannot see, and from them extracting a single macroscopic measurable parameter like temperature, that procedure is the phrase I like to attach to that is e pluribus unum. The fancy physics term for it is statistical mechanics, because you have to use a lot of stats. And Caroline is an expert on stats over here, so she knows all about that stuff. So the first line in this table, the pluribus, the thing that we're trying to figure out that we have many of, pluribus meaning many, is the gas molecules, their kinetic energies. We can't see individual molecules to measure individual kinetic energies, but we can do the math and do averages and stuff. And what we find out is that the average kinetic energy is proportional to the temperature if you measure in the Kelvin scale. And here's the formula for that. Average, let me get my gigantic cursor. Here it is. Oops. Average kinetic energy equals 3/2 times a factor K times Kelvin temperature, capital T. Now that letter K is a constant of nature. It's called the Boltzmann constant, and I'll give you a little blurb about that in just a second. But first, here's the other example that we talked about last week. Actually, 2 Tuesdays ago, before the hurricane. The idea that all those zillions, the pluribus of zillions and zillions of little teeny molecules you cannot see, exchanging momentum in their collisions with the wall of the container, produce a pressure. And the pressure is something that we can measure, right? And we talked about atmospheric pressure, 1,013.25 millibars. And talked about the hurricane. The formula that encodes that for an ideal gas, so this is kind of an idealized model, is this one. Pressure P times volume V, capital V, equals capital N times little k times capital T. Big N is the number of molecules. Little k is the Boltzmann constant. Capital T is the temperature in the Kelvin scale. Now here's a little blurb on Boltzmann's constant. It's got this weird value, 1.38066 times 10 to the minus 23 joules per Kelvin. So that's energy per unit of the thermodynamic absolute temperature scale. And it is a constant of nature. If you raise your hand if you have ever heard this term entropy, entropy. Okay, entropy is a thermodynamic term, and Boltzmann's constant is in units of entropy. Entropy is measured in units of joules per Kelvin. Here's a picture of Professor Boltzmann from Austria, and he's the one that developed the principles of statistical mechanics about 150 years ago. And looks like a guy from the Civil War, but he was over there in Austria, it was kind of controversial. A lot of people did not believe his methods were valid, but they turned out to be extremely valid and extremely useful. Here's a picture of his gravestone. Boy, does he look fierce or what? And this, you might not be able to see it. That up on top, that's the only inscription on his grave is S equals K log W. Now, that log stands for logarithms, which we're not supposed to use in this class. And we're not supposed to use calculus or trig. But K is Boltzmann's constant. S is the symbol for entropy. And W is the number of dynamical states in the ideal gas or whatever sample is, Lacey, that you're studying. So when I talk about dynamical states, I'm actually thinking about this equation. So you now know why I use that phrase all the time. Anyways, the principle of E pluribus unum traces back to Boltzmann. This is his most famous equation. Now, we're not going to make any calculations with that, but it is on his gravestone. It is a famous place in Austria, and it's worth knowing a little bit about. Okay, I want to talk about the flow of energy and the whole idea of thermal equilibrium with you for a few minutes. And let me draw to your attention or ask you to recall something that we talked about last Tuesday, and that is Joule, James Prescott Joule, his famous experiment with the paddle wheels that transferred kinetic energy to water through the pulley system and the weight that dropped down, so many centimeters of drop distance. And he was able to figure out how much kinetic energy was deposited to the water. And he correlated that to the rise in temperature of the water. Another thing that we need to know in order to figure out how things cool off and warm up is thermal equilibrium. And the formal definition is, it's kind of a negative definition, two objects that are not at the same temperature are not at thermal equilibrium. Now, let me give you an example of that. Say that you have down here in the lower right two samples of two metals or two gases or two liquids, liquid X, liquid Y, gas X, gas Y. And let's say that the temperature of X is less than the temperature of Y. So X is cooler, Y is hotter. And what that means is that the average kinetic energies in Y, the average of the kinetic energy of the molecules in Y is higher. There's more kinetic energy on average in Y than there is in X because the temperature of Y is higher. The temperature is proportional to the average kinetic energy. So on average, there's more. Over here in Y, at least to start, there's more kinetic energy. And so those faster molecules tend to migrate to X more rapidly than the slowpoke molecules go from from X over to Y. So you could draw in, now I've got a little kind of blobby shaped sample divided into X and Y. And here's a big bold arrow in red, for those of you that can see it. A big bold arrow to represent a lot of high energy average molecules bringing their kinetic energy over to the cooler sample, X. And here's the pokey. Here, in this little feeble arrow down here, the green one, to represent, all right, molecules are migrating over there to the hot substance, but they're not going, it's not as frequent because on average, they don't move as fast, okay? So there's a little bit of kinetic energy going that way, but a lot of kinetic energy going from Y to X. So eventually, the average kinetic energies are equal. And the kinetic energy swapping from X to Y still goes on, but it's now at an equal rate. And when that happens, you say that the temperatures are equal and that the two samples are at thermal equilibrium. So you no longer have to, one of them's no longer cooling and the other one's no longer warming up. They've now got to this, one starts up here at a high temperature, one starts down here at a low temperature, and eventually they swap energy and eventually they come to a thermal equilibrium. And that's where they're going to stay. If they're in a good insulated container, they're going to stay at that temperature until the cows come home. And a side note here, down here in the lower right, I just made a note that this is from chapter 6, section 10. And then overnight, you're going to have a regular homework 11 starting at 1:20 today. It's already set up. I'm way ahead of you. And I also want you to study example 2 at the end of chapter 6. So make a note of that. It's a long example of how to figure out the thermal equilibrium temperature. Now, I want to take a little time out here, and Chelsea, I think you had a question?
So if you manage to meet the requirements to be a special study group leader, how do we know when we're invited to be one?
Okay. The question was, if you've met the requirements for being a special study group leader, how do you find out if you are one or you're going to be invited to be one? And the answer to that question is, this week, hopefully, I'll finish the roundup. I'm still rounding up a few grades. And if your average is above 90% on exam 1 and 2, then I'll probably be sending a message inside web courses. Okay, and it'll say, these are the conditions for being a special study group leaders. These are the tasks. You have to do these things. And if you do these on schedule, then you get to skip the final. And so I'll probably be doing that this week sometime. So maybe by Friday you'll get a message in web courses. Okay? And Brian, I believe you had a question?
On the last test, will we get to see the correct answers now that it's over?
Okay, kind of like the exam printout that we got from exam 1. Okay, so the question was, for exam 2, are we going to get a list of what we got wrong on the test? The answer to that, kind of like the printout, you're not going to get a printout because we didn't do Scantrons. But what we are going to do is, one of my other TAs, Leah, is going to generate for every student that took the test a message in web courses that you will get in your personal private message inbox that says the number of each question that you got wrong. And then I'll publish a little blurb sheet, and you'll be able to look up the basic blurb of each question that you got wrong. So we are planning. We normally do it this way with the online class, and for this time, it's going to be we're going to use the same method. It's just like 500 and something students. It's going to take a long time to get it, but we'll get it to you. All right. Any other questions about exam 2? So. Okay, let's keep going. Now we're going to start working on heating and melting. And this is a traditional brain burner area. Usually we get to it before for exam 2, but we're a little bit behind the schedule I want it to be. That's all right. This will be on exam 3 with some other brain burners. We talked about this last week, that liquid water has this property. Every gram that you want to heat up by 1 Kelvin, it requires 1 calorie. And that quantity for water, 1.00 calorie per gram per Kelvin, that's known as the specific heat. And so we mentioned this last week. I didn't mention the fact that this number is known as the specific heat, but yeah, that's what it is. The traditional symbol is the letter C. Do not get this confused with the symbol C in the context of the speed of light, like E equals mc squared. Same symbol, just different quantity. Liquid water, C is equal to 1. Solid water, in other words, ice, C is equal to 0.5 calories per gram Kelvin. And you just, no matter what substance you have, you just measure it in the lab and try to do it as carefully as you can. Now, as we talked about last time, the difference between the liquid and the solid phase is a phase transition, and that is the point, temperature-wise, at which the average kinetic energy of the molecules is low enough, if you're cooling it, to form good, solid crystalline bonds. If you're heating, any energy that you add above that point breaks the crystalline bonds on average. You get a liquid. It's no longer solid. And those intermolecular forces, they represent quite a bit of energy. And it's actually electrical potential energy. And one way to think about that, potential energy, that's the energy of position. All right? And the energy of position means that if you're at a certain energy, you have a certain position, you have a certain energy. Now, we studied that in terms of, altitude above the surface of the earth, or altitude above the floor down here in the front of the room. But you can also think of it, with crystals. You get so close and no closer, and then at that stage, you've got a crystalline bond, because they're not moving, and you're a certain distance. Okay, so the distance is defined, and the position is defined, and it's a certain energy state, and it's electrical potential energy. So it's the electron in the water molecule, in the hydrogen end of the water, in the oxygen end of the water molecule, being attracted to the proton in the hydrogen end of the molecule. And we'll talk about molecules like that in a few weeks. But as I mentioned last Tuesday, the other, if you're talking about water, I always remember water. It's pretty easy. 1.00 for liquid water, 0.50 for solid water. I just remember that. But everything else you just look up in a table. Now, I got a problem. We did have this table last time. It has latent heat, the work necessary to force reorganization, and specific heats. And the first two are the second and third columns, but I didn't notice it last week. And this is a new table. The publisher bollocksed it up, and so go ahead, make a note that this table, I believe it's from page 93, has some typos for the water is good. Specific heats for water are good, but the other substances, they're not so good. And I'll give you some specific heats in a minute, a new table. But what I would like to emphasize to you is another way to say it. For latent heat, either latent heat of fusion for the melting, freezing phase transition, or latent heat of vaporization at a higher temperature for the boiling, condensing phase transition. every gram of a substance needs a certain amount of energy Q to melt or to vaporize. If you're increasing the heat, increasing the temperature, they'll melt or they'll vaporize. So if you're on the way up, if you're adding energy, it's melting and vaporizing. And every gram of a substance needs a little different amount. So water, 80 calories per gram for the latent heat of fusion. That's the melting, freezing phase transition. Gold, 15 calories per gram. So copper, 49. So every substance is different. The same thing over here. The specific heat, if it's not full of typographic errors, expresses the fact that every gram of a substance needs a certain amount of energy Q to raise the temperature by a Kelvin. So the specific heat is the way that we rate the energy necessary on a gram by gram basis, Kelvin for Kelvin basis. All right, and for that reason, the amount of kelvins that you heat up by, the amount of mass that you have, is important for figuring out how many calories of heat you need to heat up a substance. And so the general heating up equation is this one. And this one is one of the few equations this semester we don't have a fraction, we don't have a denominator. Q equals mc delta T. Q is the heat energy. That's the usual symbol for heat energy. M stands for the mass. How much of this substance have you got? So we measure that usually in grams. Now sometimes, if you're a civil engineer building a large concrete structure like a hydroelectric dam, you're probably thinking in metric tons. But they have to worry about the temperature and the heat stored in liquid concrete before it solidifies, so they might be working in tons, but we'll be working in grams. The other thing you got to know is the specific heat. In other words, what have you got? How easy is it to heat up? Gram for gram, Kelvin for Kelvin. So for instance, copper. Do you have copper? Metallic copper, do you have metallic lead? If it's metallic copper, okay. 0.093 calories for every gram and every Kelvin. Okay? So you multiply that. The specific heat tells you how many calories you need per gram and per Kelvin. So if you have a lot of kelvins, you need so many calories of energy. If you have so many grams, but you only want to go up by 1 Kelvin, then you have a certain number of calories. The other thing that can be varied is how much of a heating procedure do you have? In other words, how many kelvins do you have to go up? Or if you're cooling off, how many do you go down? So capital T here is the Kelvin temperature. And if you're cooling down, this will be negatory. From 280 Kelvin down to 275 Kelvin, that's a delta T of -5 kelvins. That's all right. That means you're cooling down. It's liquid water. You're cooling it down. You're chilling it. All right. So you could have a negative number for Q. That means you're extracting energy. You're cooling it off. Delta T is negative if you're cooling stuff down. The other two numbers are always positive. Specific heat is positive. The mass is positive. So the negative sign of delta T is the negative sign of Q. All right. If it does have a negative sign. So the delta T is always measured in kelvins. And you guys, if you look on the internet at various physics websites and stuff, a lot of times you'll see the specific heat rated in grams per degree Celsius. But I always like to write it grams per Kelvin. That's, to me, or calories per gram Kelvin, because I just think in kelvins. I'm an astrophysicist, so we always think in kelvins. We don't think in Celsius. Celsius is okay for planets, but if you're thinking about stars and galaxies and stuff, you got to think kelvins. All right, so here's an example. Now we're going to work this out. Easy and slow, step by step. We're going to heat up a small piece of ice, 10 grams. And then we're going to do a clicker question together with a little bit bigger chunk of ice. And this is a nice little strategy diagram to show you the process. We're going to start at a temperature below the freezing point. So T subscript I here is going to be some number below 273. And then I'm going to give you a different number over here, T subscript F, and that is going to be our final temperature. And for this example, that's going to be above 273. So we have 3 stages in this process to go from initial temperature, T subscript I, to the final temperature, T subscript F. You have to heat the solid. That's down here. This first tilted line segment represents heating the solid. So, for instance, ice. Okay, we're heating ice from below the freezing point up to the freezing point. And then at the freezing point, 273, we're going to melt all of it. So that's going to require some energy. And then once we get all of it melted, we can start increasing the temperature of the liquid. All right, so this is 2 different delta T's and then 1 melt of so many grams. And in this case, we got 10 grams. All right, so here's another way to look at it. For the first inclined tilted line segment, heating the solid, we'll just call that Q1. So many calories, whatever it happens to be. And then the next is the big one for water anyways. It's usually pretty big. Q2 is the amount of energy that you need for melting. Now that doesn't depend on the temperature. It only depends on how many grams you've got. That's where you use latent heat of fusion. So down here for Q2, you could write down latent heat of fusion. Over here for Q1, specific heat, solid water. And then, of course, you've got this last tilted line segment to represent the last part of the heating process. And we're going to symbolize that with the symbol Q3. That's the amount of energy that you need to bring the liquid water, now that you've got it all melted. It's still at 273, but it's all melted. So now you can increase the temperature up to your final temperature as liquid water. All right. Now let me pause for questions. Yes. Wait a minute. Stephanie. Right? Okay, good.
What was it you said labeling Q2 as?
What's that?
What was it that you said that were labeling Q2 as?
Q2? Yeah, Q2, latent heat of fusion in here. So this melting process, Stephanie, it's all at the same temperature. So there's no, it's all at 273 if it's water. The only thing, the amount of energy you need just depends on how many grams you've got to break apart. You go in there, you slug, a slugfest. It takes so much energy to bust all those crystalline bonds apart. It just depends on how many you got. So many per gram, and then how many grams, and that tells you. So that one's flat, but it goes horizontally, and it measures Q2. All right. Another question. I have a question for you. Let me see the clicker here. I have a quick clicker question for you. All right, get your clicker and turn it on. Go nitro. I want you to type the room number of our final exam. Room something, something, something. Let's see if these guys.
The full thing or just the last three?
The room number. Classroom, building, tomb, room, blah, blah, blah. So type that in and hit the send button. Oh, hit the refresh key.
Says no base.
No base? All right, let's try something here. All right. Yeah, I'm not getting any.
No clicks.
We should be on AA. Okay, have you got Go Nitro? All right, go ahead and answer. What the? I have no idea why that's not working. Oh, I know what we got to do. Hold on a second, students. Let's go up here to this one. I think this one's just. All right. Okay, try it. Okay, stop. All right, what room number is it? Good. Nice, I can't give extra credit if this cotton picket thing doesn't work. All right, let's keep going. Now, this is kind of our strategy diagram, all right? And by now, everybody's got it sketched in. Now, let's go through the step-by-step procedure. All right, now, I've got to give you an initial temperature. Now, this, depending on the problem that you're working on, I could give you any temperature below 273 I want. All right, let's try 266. Okay, we're going to start with some frozen water. It's pretty cold, 266 Kelvin. And let's get my final temperature just a little bit above melting point, 270. So this will be, you'll still be pretty cold. Cool and nice, 275 Kelvin. All right. Now we're going to do the two tilted line segments first, so Q1 and Q3. And then we're going to do Q2, the melting. We'll do that last. You can do them in any order that you want. All right, here we go. Q1. MC delta T. All right. So here's M, 10 grams. We know that. And the specific heat for solid water, 0.50 calories per gram Kelvin. And then from 266 up to 273, that's 7 kelvins. So this delta T over here for Q1 is 7 kelvins. All right, now notice that kelvins, capital K, cancel from delta T and then the denominator of the specific heat. And then grams cancel from the mass and the denominator of the specific heat. Question?
Is it 275 or 273?
We're heating it up to the melting point.
So wouldn't it be 9K instead of 7?
No, we're heating it up to the melting point. which is 273.
So B is separate?
Yeah, so it's you heat to the melting point, you melt, then you heat from the melting point up to your final. Okay, so it's heat, melt, heat. So in this kind of a problem, 273. I mean, if it's water, 273 is always going to be in your calculation. Okay, so that means it's 7. All right. Now this is pretty cinchy. 10 times 0.50 is 5. 5 times 7 is 35. So this is 35 calories. Okay. Now Q3, here comes, oh, what's your name again? Molly. Okay, so Molly, here's my second tilted line segment. This is Q3. And I have different numbers here. Now the mass is still the same, still 10 grams. But now I have a specific heat 1.00. And see now here I'm going, here Molly, I'm going from 273 up to 275. And there's the other 2 degrees that you were thinking about, okay? We do them here because at this temperature from 273 up to wherever you stop, you're heating up a liquid, not a solid. So you got to do a separate calculation. Now the third thing that we're going to do, it's actually part 2 of the process, is the phase transition. So from solid to liquid, that requires energy too, 80 calorie for every gram at 273 Kelvin. And so 80 calories, and we've got 10 grams. So 80 calories per gram times 10 grams. Let's see, 80 times 10. That's 800. So Q2 is 800 calories. That's just, Molly, that's just to melt it. You're not going up or down. You're at 273. That's the long, and you guys, in the strategy diagram, that's the long horizontal line segment. Okay? And it happens to be the biggest number in this example. So 800. So now we can figure out the total energy budget. And you're going to be doing, hopefully we can get this thing to work. I tell you what, can you save this image to the desktop? Oh boy. This is a problem. Quit the, you can't save it onto the desktop because you're going to have to, okay, quit the iClicker. Go ahead and quit. Okay, start it up again. All right, so let's work out, I'm sorry, we're trying to get this thing to work here. Okay, total energy budget. So you just add them up. Okay, here we go. 35 plus 800, Q2, plus 20 for Q3. And so this is kind of a cinchy one. Total of 855. Question? The 80 is the latent heat of fusion for water. That's the amount of calories per gram to break up all the crystalline bonds and give you a liquid, so many grams of liquid. Right? It goes on a gram for gram basis. Question in the back. Yeah, it's the latent heat of fusion, specific heats, all that, always in a table of some kind, or it's in the text of the problem. Question over here. Okay. Any other questions? All right. You ready to try it? All right. Let's see if we can. Yeah. Okay, here's your next question. Let's see if you guys can somebody type in an answer? Let's see if you can send it.
Okay.
Okay,
yep,
we're
that's
getting
working.
them. Okay, good. All right, now type in the right figure out the right answer. And can you turn the lights all the way on?
On.
Yeah. Okay, so just work with your neighbors and we have a few minutes for this. And I'll drink a little bit of my vitamin water. Now, Molly, we got different delta T's on this one, different, but we're still talking about everything's going around 273. So just, and hey, you guys on your homework tonight, homework 11, you're going to be tackling another version of this. So. And here we go. All right, this ought to be the biggest pile eventually. I wonder what it was.
I don't know. It's weird.
I'm glad we didn't have to sign. Oh, look at this. No. Darian signed in.
Right.
Let's see, is this the desk? How do you get to the desktop? This?
Yeah. Yeah, it's still Darian's.
Hmm. So theoretically, we could send her an email or something.
Yeah.
Send an email to Justin Bieber. Justin, I love you, Justin. Not.
Oh gosh.
Give me a fracture. Justin Bieber, please. Please, no. No Justin Bieber. JB. He's kind of a twerp. He's like a mega twerp.
Oh god.
Unbelievable. You know, it just shows you how if you have a lot of talent, you know, musical talent or something, your personality doesn't really matter.
No.
You can be a
Doesn't.
total
You can be- Oh
dweeb.
my god. He's like a giant jerk though. I mean, he apparently got his stuff together, but
Yeah. Let's get this equipment fixed up. Now, they have this. Okay, take lift that string, stool straight up. Put the seat down on the. Okay, now, this box. Goes on the seat. And this goes upside down on the flat stool. It's not going to fit. You have to rotate it. This thing's not. There you go. Okay, now. We loop it around one of the legs of the stool. Mm-hmm. Now, no. Okay, let's use our new spools. Then we get the wheel and put that on top. A liquid in there. No, it'll paste, but we want to do it. Now, this last one stabilizes the wheel. So let's keep that around there. And we better, let's get a little further. Oh, move that around the tire itself. Let's move it. All right, that's stable. Can you bring this to the back of the room? Yeah. The easy chair back there? It should be movable.
There we go.
Okay, 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Ching. And looks like you guys are doing good. Raise your hand if you got this one right. 13,620. Good. 66% of the class, so that's pretty good. All right, let's keep going. This is a good list of specific heats. Go ahead and start jotting this down. This one's kosher. It's not typoed. No, it's going to be on tables on the cover page for exam 3. Don't worry about it. And it's going to be in the homework. So, but you're going to need it for the next couple questions, so you may as well jot it down. Okay, now this next one is a multiple choice.
Oh, yeah.
Yeah, go back to presentation. Thank you.
Sure thing.
Okay. All right, next question. Which is harder to heat up? Go ahead and click start. Gram for gram and Kelvin for Kelvin. Which one's harder to heat up? It's kind of a brain burner. Unless you know what to look for. Hmm? Yeah.
Is there an E?
Who's voting for E? Don't vote for E. We had this last hour.
Yeah.
Nobody voted for.
Yeah.
Did you know this is a touch screen?
Really?
Yeah.
That's so cool.
So this is. I don't know how this is going to be graded.
Wow.
Okay, 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, stop it. Answer for this one is aluminum. And I just heard somebody over go, what? Yeah, check the numbers out. It's always amusing observing and listening to you guys. Sometimes very amusing. That's why I love teaching. Anyway, so almost always cheers me up to be in here. Yeah, what you do is you look at the specific heat for this kind of question. Because the specific heat encodes all the material properties, the density and, the charge of the nucleus and how many electrons it has in its valence band and all that stuff into one number. So for every gram of aluminum, you might want to jot this down as a sentence of what this means. For every gram of aluminum, it takes 0.215 calories to raise it by a Kelvin. Every gram of gold, it takes 0.0301, way less, to raise it by a Kelvin. And so on down the line. So that's why aluminum has the biggest specific heat of this set. And so of this set, it's the hardest one to heat up. Question?
So that means off this whole list, water's the hardest?
Yeah, water's the hardest. That's right. Off the whole list, water is the hardest. And there's not much with the bigger specific heat than water. I don't know why that should be, but you just go into the lab and you measure everything. All right, let's try another question. So, Brian.
As a consolation prize for those of us who got that one wrong, can we go back and do the first one?
No. But do try this one. You have some ice at 250 K, really cold. You want to heat it up to steam? Oh, you mean like on the homework? How many phase transitions? Go ahead and start. I almost felt like I was getting in trouble there. In the woods. 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, most of you got that one. Two-phase transitions. A lot of you voted for 3. Not really. This one you're not going back to solid, so it's not really 3-phase transitions. It's heating all the way. Notice you're not cooling back down, so you don't have to go back through another phase transition. All right, same question. What are your 3 delta T's? Go ahead and start. Multiple choice. Ten seconds. 10, 9, 8, 7. Oh, you want a little more time? Okay, 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Ding. Yeah, pretty good. And remember this when you're doing the homework. Let's dismiss early. Homework 7's ready to go at 1:20. I'll see you on Thursday. Can you turn the all on?